The inlet water temperature is used to determine whether a control action is needed to maintain the outlet water temperature. So it's the measured variable in the system. The manipulated variable, that is, the variable that's adjusted to maintain the outlet water temperature, is the steam flow into the heater. The feed-forward control system works like this. If the temperature of the water entering the heater changes, the primary element in the system, in this case, a temperature-sensing bulb, detects the change in temperature and changes the signal that it sends to a transmitter. The transmitter measures the signal from the temperature-sensing bulb and sends a proportional signal to a controller. The controller measures the signal from the transmitter and compares it to set point. If there's a difference between the two values, the controller sends a signal to the final control element in the system, the control valve. The control valve responds by opening or closing to change the amount of steam flow to the heater. If the temperature of the water flowing to the heater decreases, the control system opens the control valve to increase the steam flow to the heater. This provides more heat for transfer to the water and prevents the outlet water temperature from dropping below its desired value. Now, if the temperature of the water entering the heater increases, the control system closes the control valve to allow less steam to enter the heater. As a result, less heat is transferred to the water, and the outlet water temperature is kept from rising above its desired value. A feed-forward control system can be effective at correcting for certain process disturbances before the disturbance affects the controlled variable in the process. However, there are many possible disturbances in a process, and a typical feed-forward control system may not be able to respond to every one of them. For example, the feed-forward control system that we just looked at responds only to changes in the temperature of the water entering the heater. Other disturbances, such as a change in the pressure or temperature of the steam entering the heater, can also affect the outlet water temperature. But those disturbances will go unnoticed by the feed-forward control system. To correct for those types of disturbances, a combination of feedback and feed-forward control could be used. With combined control, the feed-forward part of the system responds to changes in the inlet water temperature, while the feedback part responds to changes in the outlet water temperature caused by other disturbances. By combining the features of feedback and feed-forward control, greater control over disturbances upstream of the process and within the process can be attained. In this topic, we saw how the four elements of an automatic control system work together to control a process, and how a control system responds to a process disturbance. We also saw how feedback control, feed-forward control, and a combination of the two methods work to control a process. Now let's try some practice questions related to this material. Right. The controlling element, or controller, computes the difference between the measured level and set point, and sends a corrective signal to the final control element. No. The controlling element, or controller, computes the difference between the measured level and set point, and sends a corrective signal to the final control element. The controlling element, or controller, measures the signal from the transmitter, compares the signal to the desired level setting, computes any difference between the two values, and if necessary, produces a corrective signal. The controller sends the corrective signal to the final control element, which in this case is a control valve. One of the basic methods of control used by automatic process control systems is feedback control. In a feedback control system, a control action is initiated after the controlled variable has deviated. A feed-forward control system attempts to correct for a process disturbance before the controlled variable in the process deviates from set point. All processes have characteristics that can affect how a control system responds to operating changes. Two of the more important of these characteristics are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in describing electrical circuits, they can also be applied to process systems that contain fluids. For example, in this system, the resistance is caused primarily by a valve that opposes the flow of liquid from a container. The system's capacitance, or ability to store energy, is determined by the size of the container. These same characteristics can also be applied to gas or vapor systems. For example, in this system, the resistance is caused primarily by a valve that opposes the flow of gas from a pressurized cylinder. The capacitance depends on the storage capacity of the cylinder. Now, in a thermal process, that is, one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. The amount of heat or thermal energy that the liquid is able to store represents the capacitance of the system. Process characteristics such as resistance and capacitance can affect how a control system responds to process disturbances. We can get a better understanding of how these characteristics can affect a system by looking at an illustration of a simple heat exchange process. In this system, steam flows through tubes in a heater and heats water that flows around the tubes. At the moment, the temperature of the steam entering the heater is 400 degrees Fahrenheit, and the temperature of the water leaving the heater is 200 degrees Fahrenheit. Now, suppose a process disturbance causes the temperature of the steam to suddenly rise to 500 degrees. What do you suppose will happen to the temperature of the water? Even though the steam temperature increased suddenly, the water temperature will remain unchanged briefly, then increase slowly. It's easier to see how the water temperature changes by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input or a step change. When we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. In the heater, the transfer of heat from the steam to the water was delayed because of resistance to heat transfer through the tubes and because of the water's capacitance, or the ability of the water to store heat. Another factor that can contribute to dead time is the distance that the heat has to travel to reach the temperature gauge. In this case, the greater the distance from the heater to the gauge, the greater the dead time. Looking back at the graph, we see that after the time delay, the water temperature gradually rose to a new value of 300 degrees. The total amount of time that passed from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag time, or lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance.